Hey there, this is physics lesson 4.06, free body diagrams. And today we're going to be talking about how to draw a free body diagram, and the definition of a free body diagram is a diagram of all the external forces on an object. And we can talk about some of the rules for free body diagrams. So let's start there. So rule number one, vectors should be to scale. So if you have a 100 Newton vector and a 50 Newton vector, the 50 Newton should be half as big as the 100 Newton. Two, for straight line motion or translational motion, vectors start at the center of mass. All right, and then we'll add more rules as we go. So let's look at some samples. All right, in the last one on Newton's third law, we did a box on a table. And luckily for me, rule number 3 is we often represent the object, whatever it is, whether it's a car, whether it's a person, whether it's a desk, as a box. So luckily for me, who doesn't draw well, everything's a box. So sample number 1, let's do a computer sitting on a desk. Take an easy one. So, gosh, look at that. I even screwed up my box. Leave it to me to screw up a box. For this one, so my center of mass is going to be here, and I always draw, and I write my vector that's due to gravity as F sub W, because that's mass times gravity. I always draw that one first, because if we look at an object in different, we might take the same object and draw 3 different body diagrams for it. The weight vector is always going to be the same because it's mass times acceleration due to gravity. The mass of the box usually doesn't change, and acceleration due to gravity never changes unless we change elevation. So again, I recommend drawing your weight vector first. Now, I can't just slap any old vector on here. Let's do the motion analysis. And remember, I always do my motion analysis in green. And so the X means I'm not moving, it's at rest. So I better have a net force of 0. So if this is about that far, this needs to be about that far. And this is the normal force, the table, the desk pushing up on the computer at a 90-degree angle. So I have gravity pulling down on the computer, and I have normal force pushing up. But notice these had to be equal and opposite. If I'd made that shorter, that would have implied that the force of gravity was stronger and the computer had broken through and was going to drop to the floor. All right, let's look at sample 2. Let's do a puck on an air hockey table. Puck moving on an air hockey table. So I would say rule number 5 is start with a force motion analysis. So right away, when I start to think of that, I can see that the sample problem I came up with has a problem. Puck moving on an air hockey table with constant velocity. I didn't have enough detail. Okay, so take a second and tell me what forces do you think, and if you've ever played air hockey, you know that you knock the puck back and forth. So take a second and think about this, puck moving on an air hockey table with constant velocity, and tell me what forces are going to be at work. All right, hopefully you said gravity, the weight. Hopefully you said normal force. Did you say the force of the striker on the puck? Doesn't say anything in the problem about the striker on the puck. So the other thing I know, let's get this. I'm going to start abbreviating constant velocity to CV. It doesn't say that I'm striking the puck and getting it to move. It just says the puck's moving on an air hockey table with constant velocity. That's the same free body diagram as if it's sitting still. That constant velocity implies there's no acceleration. And the only time the force of the, I don't know what you call what do you call the thing you hit him with? I don't even know. The only time that force comes into play is when it's in contact. Remember, that's an applied force. It's a contact force. It's not saying anything about that. Well, you might have said friction. Here's the thing with that. Realistically, there's always friction, but the reason I picked an air hockey table is there's so little friction, we usually ignore it. So if you said friction, technically you wouldn't be wrong. But in this case, if you see on ice, if you see air hockey table, there's a pretty good chance that we're going to ignore friction. Okay, let's do another. So yeah, it would be the same free body diagram. Here we go. Sample 3. Okay, sorry about this. I paused the video to take a sip of water and I forgot the video was paused. So I wrote the next problem down. I'll let you guys catch up. Okay, the other thing I've been a little bit remiss about is doing coordinate systems. So let's get a coordinate system here. And let's say my motion is this way, and this time, look at this, I've got acceleration. So my motion's going to be this way, and I'm going to have acceleration. So what are my forces that are going to be at work here? Do a force motion analysis and see what you come up with. Pause the video if you want to. All right, I'm going to have gravity. I'm going to have the normal force. I'm going to have an applied force because there has to be something that's causing my car to accelerate this way. And the reason I added rough country road is that's also going to give us friction. So I'm going to have 4 forces this time. Now the trick is I can't just slap vectors on. I have to do this to scale. All right, so here we go. Let's do a box. And I'm going to kind of write down my thought process as I go. So I'm going to do my weight vector first. So here's the thing with this weight vector. If it's a 100 kilogram car, the weight is mass times acceleration due to gravity. So let's round 9.8 up to 10. That means that this is going to be a negative 1,000 Newton vector. Okay, so this is my car and my road's down here. All right, well, we've been drawing the normal force as equal and opposite, but that's not always the case. If the car hit a bump and it caused the car to go up in the air, all of a sudden now I have acceleration this way. So you have to pay attention to where your motion is. All of my acceleration is this way. There's no indication that the car is traveling vertically at all. So my normal force vector has to be equal and opposite to this. So let me see about that. Let me add something up here too. Let me give a value to that. So let's say we've got a 100 kilogram car accelerating with a 500 Newton applied force down a country road. Okay, so now I'm ready to put in my, so what were my steps here? Let me list out some steps. So step number 1, I did my weight vector. 2, I had to determine how big my normal force should be. So I did my Fn next. And I knew that had to be equal and opposite. All right, now the problem tells me I have a 500 Newton applied force, and that's causing the acceleration. My acceleration is this way, so my 500 Newton applied force has to be this way. If this is a 1,000 Newton vector, then this better be about half. So FA, and that's around 500 Newtons. There are going to be tests where I'll actually get out a ruler and I will check your free body diagrams. Okay, well now I have friction. Can I just put in a vector that's the same length as this? Did you say yes? If I drew in a vector that was equal to this, what would be the implication to that? That would mean that I don't have an unbalanced force, that my forces are balanced. So if I draw this vector equal and opposite to that, I can't have acceleration. To have acceleration, I have to have an unbalanced force. So I have to draw this this friction vector. I don't know what the value is, but it has to be smaller than my applied force vector. So after I did my normal force, I did my applied force to scale. And then finally, I did my friction force to match my motion. Well, how did I bring all that together? Your force motion analysis. I have acceleration in the horizontal, so I have to have an unbalanced force in the horizontal. I know that this is 500. I know that this is around 1,000. My vertical has no motion, so those forces have to be equal and opposite. This takes practice. You're going to get a lot of practice doing this in the next chapter. Most of our free body diagrams are going to look like this. All right, let's do one more. All right, let's do a last one. And I'm going to have you guys try this one, and then I'll write the answer out. Sample 4. A box sliding to rest. All right, pause the video and see if you can draw this free body diagram. Correct. Let me give you some parameters. Let's say that's the direction of our motion. All right, take a crack, pause the video. Okay, welcome back. If you said, I've got gravity, I've got normal force that's equal and opposite to gravity. And if I'm moving this way, but I'm slowing down, I have deceleration, so I have acceleration. Actually, the acceleration is that way. The motion is this way. So I have to be careful when I write acceleration above. So what that means is if I'm moving this way, friction tends to slow me down, so my friction vector has to go this way. And I don't know yet, we don't know how to calculate frictions. We can't tell how big that has to be, but it's probably going to be smaller than these two. So if you put that, you had a correct free body diagram. Congratulations. Okay, you've got some practice problems for these, and this is also the last topic for this chapter, so we'll be ready for chapter review and test. All right, that's all we've got for now.